We have so far talked about vectors in Minkowski space and how their components transform under basis changes. In this video, we will expand this to general tensors in Minkowski space. We start by defining the outer product or tensor product between two vectors v and w as a bilinear multiplication. This means that it is linear in both arguments. For example, if we take the outer product between v and a1w1 plus a2w2, this is equal to a1 times the outer product of v and w1 plus a2 times the outer product of v and w2. A similar linear relationship must hold for the first vector. The tensor product space can now be formed as the set of linear combinations of these outer products. Given a set of basis vectors, e mu, a basis for the tensor space can be constructed as e mu nu is equal to e mu o times e nu. A general tensor T may now be written in terms of this tensor basis, using components with two indices, one for each index in the basis. Again, we are using the Einstein summation convention to sum over the repeated indices, here mu and nu. Of course, the choice of e mu as the vector basis was arbitrary, and we could just as well have used a different vector basis e mu prime, leading to a different tensor basis e prime mu prime nu prime. Just as we deduced the transformation properties of the vector basis in the previous videos, we now wish to relate the two different tensor bases to each other. In order to do this, we can use our knowledge of how the vector basis transforms. Inserting this into the definition of the tensor basis, we can use the linear property of the outer product and find that e mu nu is equal to lambda mu prime mu, lambda nu prime nu, e prime mu prime nu prime. Just as vectors do not depend on the basis used to describe them leads to relations between the vector components in different bases, we can also use the fact that a tensor does not depend on the basis used to describe it. We must therefore have that the general tensor T can be written in either the unprimed or primed basis, and that these expressions must be equivalent. Inserting our expression for e mu nu in terms of e prime mu prime nu prime, and using that the basis tensors are linearly independent, we can identify that T mu prime nu prime is equal to lambda mu prime mu, lambda nu prime nu, T mu nu. Compared with the corresponding transformation relation for the vector components, we see that we have one set of transformation coefficients for each index of the component, while the vector with one index is multiplied by one transformation coefficient. Our tensor component with two indices is multiplied by 2. In this example, we have been working with the outer product of two vectors, and the components having the above transformation property are the contravariant components of a rank 2 tensor. The generalization to outer products between three or more vectors is straightforward, resulting in higher rank tensors whose components transform with a corresponding number of transformation coefficients.